Welcome back, everybody. So this is the story of last year project here at the Colourlab, where I developed a multispectral imaging system for photography and film. But today I want to try to propose this multispectral system not only for film and photography, but also for other kind of transmissive objects. First of all, so you see the thing first. This is the multispectral system. This is the illumination system. These are the slides that I used mostly at the first experiments. Graphic slides. This is the camera, lens, and sensor. And here is a close-up of the film gate. As I said, today I will not only talk about photography and film, but I also use these samples that David already showed. Other of the same set that was used for this research. And but let me go back just briefly. Sorry for those who already heard this story, but not all of you attendees heard it, so I have to give a reasoning why I started this project at the Colourlab for film and motion pictures. It's important to distinguish in film between the material essence of film and the visualization event. The first is a series of images impressed on a plastic strip. And the second is a moving picture of big screen. So there's a huge magnification factor in between. There's motion that appears, and two different things. And two different perceptions. When we digitize the film, basically what we are trying to do is to replicate the visualization event in a way that this observer here that is watching the projection of the analog film, after this digitalization of the film and the projection with digital tools, we'll see hopefully the same thing. To do this, it's very important to analyze what happens to the film when it is projected on the big screen. For example, we have here this Keynote film projector, widely used from the 70s and the 80s. The light bulb is a xenon arc bulb that is positioned in the focus of an elliptical mirror that we see here. This because the no light can be wasted, because you have to imagine that 24 millimeters of film end up being in something big or even bigger than this screen that we are seeing here. So the intensity of light has to be a lot, so no light can be wasted. So all the light rays coming from the bulb have to enter in the gate and illuminate the film. This is a completely different situation because here the film is illuminated with a diffuse illumination, a soft diffuse illumination in which the light rays are coming from all directions, while in projection, all the light is very highly directional. All film scanners use diffuse illumination because of several reasons. It's easy to have homogeneous illumination on the film, and then dust and scratches are less visible. This is a commercial from a film scanner manufacturer that is showing how diffuse illumination is better than condensed illumination, because those red rays here are not collected by the imaging lens, and therefore this scratch will be more visible, darker, and therefore more visible in the final image. And this is not the case here, because we have these green rays that are scattered, are deviated by the scratch, but they make it to the imaging lens. This is the typical difference between condensed and diffuse illumination of the same film captured with the same system, aiming at the same white point, at the same exposure, but two different kinds of illumination. So dust and scratches, way more visible in the condensed illumination, contrast way higher in the condensed illumination, and diffuse illumination that is a sort of automatic restoration of dust and scratches that are less visible, and this image that is a bit softer. We can explain this difference, for example, with this example, when we illuminate such origami with a directed illumination, meaning with the light comes from a distance, like from the sun on a clear day, the shadows are very strong, very well-defined and sharp. And this is not the case in the situation in which the light is coming from many directions. When we look at this image, I think it's quite subtle, but I think you can agree with me that the difference is not only in dust and scratches and contrast, but there's also a shift in hue, with the diffuse illumination being bluer, cyan, and a little stronger touch of green in the condensed illumination. This kind of difference have been observed a lot in motion pictures, especially for film toning. We have the example of this film in which the background of this blue that you can clearly see when you handle the film is kind of disappeared when you project the film. And this is due to the fact that short wavelengths are scattered more than longer wavelengths. You can see this, the sunset, for example, when the sunset is orange, because the blue short wavelength component of daylight are scattered away. So the remaining that reaches us is the opposite component, the orange one. Then another topic that convinced us to build this multispectral system due to these two different types of spectral bands that you see in color imaging systems. Mostly film scanners, many of them tend to use these narrow RGB bands with these parts that are not covered by the sensitivity of the system, while the majority of color sensors use spectral bands that overlap. And in this way, we can have colors that are in a way closer to the colors we see and we perceive. So why multispectral, why film scanners use these narrow bands? Because they aim at matching the peak of sensitivities of typical modern film stock, which is made of cyan, magenta, and yellow dyes. So with these narrow bands, as you see in this plot, they are aiming at these peaks of absorption. This has an advantage, for example, when you capture color negatives, because you're not interested in the accurate look of these negatives, you're interested only in the final result of the print. And then, for example, another it's the other one. Okay. Another example of the advantage of narrow spectral bands is for faded prints, a very diffuse case that a very important threat to the heritage on chromogenic film. If you want to restore the color of this image, is very important, the starting point. And the starting point is also determined by the spectral bands of your RGB imaging system. If you have low color separation, meaning that you have overlaps between RG and B sensitivities, you get out less color than if you have this very selective RG and B with narrow spectral bands and with no overlap.
This one is
narrow spectral bands, high color separation, broad spectral band, low color separation. Yeah, more color accuracy, but here it's faded. So who cares about color accuracy? What we want to achieve is a good digital restoration. And here, more, let's say, color information that is extracted from the film. This comes with many drawbacks. One of these being this blind spot, especially between the green and the red sensitivity. And sometimes some colors are just not detected because they are in this blind spot. And then another problem is that if you capture a print and this print is good, is really what you want to reproduce, then you get colors that are too vivid. For example, here in this, I don't know if I can start it. I'm just flickering between high color separation and low color separation. When you see these vivid colors, is the high color separation that emphasizes the color saturation, but emphasizes it too much because when you handle the film, you don't see those vivid colors. It's just an excessive enhancement of color saturation. So for all these reasons, we build this. We have this. This was a 3D printed sphere with the LED that are shining inside the sphere. This is the film gate in which you have the diffuser. That if the diffuser is inserted, you have diffuse illumination. You remove the diffuser, you have condensed illumination because of these lenses that are below it. Yeah, these are the LEDs that are shining inside the sphere. That then, of course, is not like this; is closed. But just to let you see the guts of this system, I showed you open. These are the parts, the 3D printed parts. Of course, the integrating sphere had to be coated in the inner side of the integrated sphere had to be coated with white. No, because if there is a bit of roughness, the coating it sticks a bit better. So it was better not to have polyester. I applied something like 20 layers. Yeah, because the importance is that this coating then has a sort of optical infinity thickness, because you don't want to the light to be lost, and it's kind of transmitted out of the coating. This is you get the indications from the vendor of this liquid spectrum, let's call it like this. And yeah, you have to apply many layers before reaching this infinity thickness. Some words about this, the optical design. Anyway, there are these two, very quickly, these two lenses that are creating the image of the exit of the sphere at the entrance, at the pupil of the imaging lens. And then, so you have this sort of optical configuration in condensed illumination, in which basically each point of the film receives light just from one direction only. And then the light is collected also with a very limited range of angles, depending on the aperture of the imaging lens and the working distance of the whole setup. And then you introduce the diffuser, and all of a sudden the light comes from many directions. So in a way that each point of the film is illuminated more or less 180 degrees. These are the spectral bands chosen. There were 10. And two of them, these dotted ones, had to be created with an interference filter that is filtering a broadband LED. This because you don't find efficient LEDs between basically 530 and 600 nanometers. And in this set is also included the RGB narrow bands. So you can get either color accuracy with a full range or maximize the extracted color information with the selection of just these three RGB. So spatial resolution is very high because we had a 60 megapixel monochrome CMOS, also with a quite good depth, because the analog digital converter already is at 16 bits because of very low readout noise, so very high dynamic range. And in our setup here, we have 0.68 X magnification equivalent to 4,500 pixels per inch. So in this full image, if we take these details, we can even read this crystal clear polyethylene. So the spectral resolution is very good. The spatial resolution, sorry. The spectral resolution is not as good. It's always a trade between the two. So with our 10 spectral bands, we have 27 spectral step between 415 and 660 nanometers. These are the spectra of these selected. The average spectra of the pixels of this yellow part, of this red part, and this green part that you see here in this plot. So I wanted to test this on these samples, just curious to see what's coming out. I put this here on the diffuser. I took a measurement with the diffuser, but also without the diffuser. I use these 4 samples. Please. No, this is the diffuser. Basically, in this case, the sample is on the diffuser. Yeah, and of course, when I removed the diffuser, I put it on the last lens, and then I had to refocus, of course, because the position was different in the end. But yeah, I did both measurements. So I gave this name milk topaz ice amber. Of course, they are not real gemstones. They look like these are the names that came in my mind to describe it. Samples. Here we see the colorimetric images calculated from the multispectral capture. A very particular color, I would say. We can maybe comment later on this. This is, let's say, the a detail magnified, in which we have a different metric scale. So this is now 53 millimeters. And the transmittance factors. The milk one is the least transmitting because it scatters a lot. Let's say there's no real. If we go here, we see here we read nothing underneath. Here we read very well. Here we read something. I don't know if you see, but you can see the ink underneath, and here almost nothing.
No, you use a calculate the transmittance factor.
It's a flat fielding operation that is done with white, meaning with the.
The white is the diffuse.
No, the white meaning the white in transmittance measurement. The name without sample.
Yes.
Yeah.
But then without sample, but then you still have the diffuser.
Yes. Yeah. If you measure the transmittance in diffuse illumination, the diffuser has to be also in the white. No. It's kind of, because the diffuser is in both moment, white and film, so its contribution is compensated in the ratio.
Sample is equal to the sensor.
Yeah. Yes. Yeah. the camera is up.
No, but just, sorry.
No,
But then
it's
you
a
still
workshop.
have-
So
You still have the diffuser between the light source and the sample, right?
Diffuser is a part of the light source.
yes,
But
yes,
you cannot do the measurements without diffuser.
yes, because the images in condensed illumination are without the diffuser, and there's another white.
Okay, so in your transmittance factor calculation, the light coming out of the diffuser is the light which is being transmitted. That's the answer.
Yes.
And now there is a line.
Yeah.
But if it was the other scenario, then you have to take out the diffuser, and that's what is.
Yeah. And I made another white for this other configuration. So diffuse illumination, magnified, transmittance factors. I don't call it transmittance spectra because the resolution is so limited that maybe it's better to call it factor. And as we were seeing, the topaz is the most transmitting one. And then we have ice, and then amber, and then milk is the least transmitting element. Condensed illumination, darker colors, zoom, spectra, and comparison. So I think this is the most interesting. We see milk is way darker. Of course, this is condensed illumination. This is diffuse illumination. Here we barely see anything. Nothing. No, barely see anything. And I think that there is a difference here in the spectra. The spectrum is the average of the whole sample. And I believe this decrement is mostly due to the imperfections, and because the sample is really transparent, is absorbing because it's colored, but it's not scattering. And in this case, the geometry of illumination by definition shouldn't play a role, and that's what we see here. More difference in the eyes sample, and more or less the same difference visually in the amber sample. Here we see the spectra. Diamonds are condensed illumination, and circles are diffuse illumination.
Condensed illumination is bottom right, top left, huge square.
Yeah, top left, condensed illumination, bottom right, diffuse illumination.
So the diffuse is transmitting
More, yeah. Then I thought it was also interesting to compare, to do some reflectance measurements. And here there are different approaches to do this reflectance measurements on partly transmitting objects. In my case, indeed, I chose to place my sample with nothing underneath. So there were these, now with the new, for paintings, the new system for painting, the art scan, you can place your object in a way that behind it, that there's nothing, let's say light can go through. So that's what I did here. let's say, different approach than the typical black background, which is used, for example, in these Camus captures, or in which you want to measure the transmittance of the the reflectance of the transmissive object, because of course then if the object transmits something, you will always something that comes back not as a reflectance but as a double transmittance. So to avoid this and measure pure reflectance, you want to find a way to avoid this double transmittance that comes back and is collected by the sensor. Ideally, you have the outer space in which there's nothing. Of course, there's always a wall. Is black likely in the lab, but I think it's still a bit better than have, because perfect black doesn't exist. So I think is instead of having directly in contact with the object, it's better to let the light go away as much as possible. Then you have to be sure that it really goes away. And of course, having a black wall helps. Maybe ideally you would have a hole, and then this light goes in another space in a way that it's really lost. Yeah, you can have all sorts of creativities in this way. Anyway, a couple of these are the reflectance factors. Now the blue is the darkest. It was the brightest in the other measurement of transmittance. Here is the darkest, and the white that was the blackest. The milk that was the blackest in the transmittant measurements. Now is the brightest, and this is no surprise. And this is the comparison between transmittance factor and reflectance factor. I think it's quite interesting. I still didn't think too much of the other. There was no time. I did this measurement last week. And so topaz and milk are basically inverted in the two. But in the middle, ice and amber, more or less, they look the same, and they have the same relation between the two, in the sense that if you look at them through or in reflection mode, they have the same, I got the same numbers, let's say the same spectrum. While with the other two samples, the situation is exactly opposite. This is what I wanted to say today. And of course, again, it's a workshop, so I would like you to comment. And, you already did.